Everyone, welcome to learning Python. We'll start with doing some simple computation on how we can compute evaporation, not the evapotranspiration. We'll go into transpiration part later. So like you might have experience when you dry your clothes. Typically you put your clothes either in the sun, or if there is no sun outside, you put in your room and then you increase the fan speed. So basically there are two mechanisms, either through the radiation, your evaporation is taking place from your cloth, or you are creating this wind energy, or this gradient you are creating in the humidity, and because of which the evaporation is taking place. So these are the two mechanism. In this beginning of exercise, we are treating that separately, but we use both because we need both to get the evaporation from any water body or from anywhere we have the water. So these are some simple formulas are given in this. You can read about both the approaches. So ER is evaporation due to the energy we have put, you know and then we have the EA. This is based on the aerodynamics, or how the wind speed is. So these both formulas are given. The idea here is not to teach so much of hydrology. You can go through this formula. In the book it's given and it's taken directly from the Van to Chow. You can read more about it from the Van to Chow. And here we have the combined approach, how we can combine optimally this based on the aerodynamics approach and based on the net radiation approach. One more thing we'll do, we are doing lots of things based on the synthetic data, so that I don't have to distribute any data, and you can generate your data. We have been using standard normal distribution, and we have been using standard uniform distribution. Standard uniform distribution means my minimum value is 0, maximum is 1. But if I want, I can, if we want, we can transform it from 0, 1 to any A and B. So simply what we'll have to do, you can define A, you can use this formula, A plus B minus A, the range, the difference we need, multiplied by X old. X old is uniform distribution having range of 0 and 1. In fact, any data with the minimum range of 0 and 1 can be transformed to range of A and B by using this formula. You can transform from A and B to some C and D also, will maybe sometime discuss. So we'll generate some random uniform distribution, and will with the range of A and B. There are some libraries in Python where you can directly generate A and B, but it's good to learn how we can transform it. Similarly, we have been using standard normal distribution with mean of 0 and standard deviation or variance of 1. Here also we can transform the mean and we can transform the variance. So you can use this formula. Let's say new mean you need is mu, so you can use mu plus whatever new sigma you need. So if you have a variable having mean 0, variance 1, you can transform, variance will become square of sigma. So it's the standard deviation we can define. Now let's go to the Python and play with this. So first we'll generate some data. So we are generating some value for the net radiation with upper bound of 150 and 250. So it can be any value, it can take between 150 and 250. So how we define? We define the minimum range, that is the 150, plus difference of both the range, that is 100, multiplied by this random number. Here we are defining with mean of 25 and standard deviation of 3, the way we discussed how we can compute. So now we are taking not the standard normal distribution or the standard uniform distribution. We are defining our own range, we are defining our own mean and standard deviation, or we are defining our own parameter. We'll take some standard constant with reasonable value, not some random value. First time it takes time. Sometime I rerun it. I run it before starting the exercise, so it moves fast. Sometime it takes time when I'm doing first time. So now we can compute our evaporation due to net radiation, which is called ER. And remember, we are using this multiplication operator. So we could have written ER is equal to ER multiplied by this number, or we can compute. Largely this rainfall and PT we deal with daily data, so we can have our output in terms of the how many per day we are getting. Let's print it and see how much value we have got. So all the values are about close to 7. Similarly, we can apply our aerodynamics approach and we can compute this. Also we are converting into per day, and let's look at. So these values are going up to 13. This I can see maybe and as low as close to 0. So we see huge variation. Now we will combine both the approaches. So we compute our delta and we can see how this looks like. So in the next we'll generate the histogram. So first we learned how we can compute evaporation due to energy approach, then due to the aerodynamics approach. We combine both. Here what we will try to do, we'll create 4 subplot. So it's the same figure, like we define our matrix with 1 by 2, 2 by 3, whatever row and matrix. Here also what we are telling, create subplot. Our matrix is going to be 2 cross 2, and this is the first, then second, third and fourth, because 2 cross means 2 cross 2 means we can have 4 we can have the 4 plot in this, or 4 elements are there. So first we are plotting the ER, evaporation due to net radiation, then evaporation due to the aerodynamics, then the total evaporation, and then how much weightage we are giving. So we can look at this plot. So this, the way we defined subplot is, this is the first entry, second, and then third and fourth. So it goes from left hand to side to right hand side, and then top to down. So you can keep on defining. You can use any 3 by 3, 2 by 3, any you can use, and you can generate more plot. Many times we need to generate 2 plot. Let's say for the same time we want to see how is rainfall, how is the PT. We can plot in different plots for more clarity, because the ranges are different. You will see more and more such kind of plot. So one more thing you can see in this, you look at the value of EA, which is our Y label for this, and this is our ratio of ER by E, or the our weight. These are not, we cannot read it clearly because there is a overlap. So we can use one functionality, subplots adjust, and we will create so much space. So you can see now there is more space, so we can very clearly read. So you can play with this parameter, try different value, and whatever best fit your subplot, you can choose that number, so that clearly all the labels you can read. So in this exercise we learned how to use subplot, which is required many time, and how we can adjust the white space between different figures, so that we can read it clearly. Thank you, and then see you in the next session.